Hey everyone, in this video I'm going to go over questions 25 to 30 of the USNCO 2025 local test. So this is the kinetics part of the test, and you can follow along with both the exam and the solutions document I've written in the description below. So let's start with question 25. This is an application of relative rates. So it's asking us to find the equation that signifies how concentrations are changing. So relative rates comes from the conservation of mass. And that essentially requires that as the reactants are losing mass, the products are gaining that mass. So you can intuitively see how you get this relative rates form, and this is essentially balancing the coefficient with the rate. So this ensures that the conservation of mass applies, since, for example, if it was like the other way around, if it was not 1 over A, but it was regular A, then if the coefficient here was bigger, it would far exceed the mass loss or the mass gain of the other side. If that makes sense. It's a bit hard to explain relative rates, but I'm sure that you guys see this intuitively, so I'm not going to bore you too much about it. It's pretty introductory in AP Chem and stuff. So we're just simply going to apply this relative rates thing, and looking at the coefficients that we have I minus here, which has a coefficient of 8, and that's going to be our A here, and our I3 minus is going to have a coefficient of 3, so it's going to be 3. So looking at this, we're going to want to have 1 over 8, and then 1 over 3, but negative on this side. And that's rearranging. We're going to multiply this by negative 3, this by 8, and we're ultimately going to get this right here if you do that multiplication. So that's going to be our answer. And you can see intuitively here how this balances out the conservation of mass, because this has a coefficient of 8, so it's going to be losing mass 8 times faster than this is gaining mass. So the coefficients of 8 and 3 here help balance it out. Now let's move on to question 26. So question 26 is where you need to know your rate laws, and you're going to need them for the rest of this section, essentially. You need to know your second order integrated rate law as well. So as we can see here, the rate is K times carbon monoxide times chlorine, and it's saying that there's equal molar quantities of both of them. So we can essentially substitute one for the other. Let's say that we substitute this here because Cl2 equals CO, at least in terms of the initial concentrations, because that's what the question says. So if you notice this here, the order of this is going to be 2 because that's the sum of the exponents. So you need to know your second order integrated rate law, which is this right here. And if you notice this is in the form y equals mx plus b. This is going to be constant since it's determined based on the initial concentrations, not the concentrations throughout the reaction. So the m here is going to be k, the y is going to be 1 over CO. It's asking what's changing linearly with t, and the x is going to be t in this scenario. So it's asking what's the y essentially here, and that's going to be 1 over the concentration of carbon monoxide. So our answer is going to be C. Okay, let's move on to question 27. So question 27, you need to use the first order decay law, and that's going to be A equals A, the initial A times e to the power of negative kt. So let's rearrange for k, since we're going to apply this equation. So you pretty much need to know both of these equations. This is just saying that the half-life here of the substance is going to be equal to ln2 over k. So we first need to solve for k and then plug it into here. So rearranging this equation, we have k equals negative 1 over t ln a over a0. You can pause to see how I got that. It's just doing some algebraic manipulation. And we have all of these values here. For t, notice that the sample is first measured in 1925 and then measured in 2025, which has a difference of 100 years. So that's going to be our t. And then a is going to be this here. That's the current activity. And then this is going to be our initial activity. So we're just going to plug that in here. I've just plugged those numbers in and done the computation. So you get this value for k. And now, like I said earlier, we're going to use this equation to find the half-life. And plugging our k value in here, ln2 is 0.693 approximately. That's going to get us 1600 years. So that's going to be our answer. So let's move on to question 28. Question 28, let me zoom out a bit. Question 28 is asking what the activity, activation energy of this reaction is. So for this, you need to know the Arrhenius equation. I believe this is actually given in the packet, in the test packet, but I could be wrong about that. This is the Arrhenius equation, or at least the ln form of it. And if you notice here, this is essentially also y equals mx plus b. This is our y, negative EA over r is our m, 1 over t is our x, and this is constant, so it's our b. And if you notice, that's actually verified by this graph here. ln k is our y-axis, 1 over t here is our x-axis. So it's asking for the activation energy, and that's going to come from our slope, which is negative EA over r, and it actually gives us the slope value, negative 4,253.9. So to find our EA, we're just going to do some calculations here. And plugging in r equals 8.314. We've done the computation here. That's going to get us this value, and that's going to be our answer. Okay, moving on to question 29. This is a pretty good problem in my opinion. It combines a lot of key kinetic concepts. It's going to have you do steady state approximation, multi-step reactions, general rate laws, all that stuff, and you're going to combine that to get the solution to this problem. So let's break down what the question is asking, because it's kind of complex to look at this initially. So it's asking us to get the rate law into this form here, and then actually solve for the value of that rate constant in terms of this here from the problem. So let's get into it. So you'll notice that the reaction is going to propene, which is this here. And if we write the rate law for this, the initial rate law, we get K2 times the intermediate diradical. You don't need to worry too much about what an intermediate diradical is for now. And that's just because of this reaction here. The general rate law is just the rate constant times whatever is on the reactant side. So that clearly doesn't match the form we're asked about in the question. So let's get to how we actually get there. What we need to do is apply the steady state approximation. And if you're unfamiliar with what that is, that's essentially saying that the intermediate rate of formation is 0 since it doesn't accumulate. The intermediate in this case is going to be our intermediate diradical. So we're going to say that the net formation rate of that is going to be 0. That's an approximation, of course, but it's one that we must do to solve the problem. So let's break down what is causing the formation of this a diradical, and then we're going to subtract it by what the diradical is turning into. So if we notice here, this cyclo C3H6 is going to turn into the intermediate diradical with the rate constant K1. However, the reverse is also true. The intermediate diradical is going to form cyclo C3H6 with the K-1 rate constant. And the same thing is going to apply here. The intermediate diradical is forming propene with the rate constant K2. So in order to approximate that formation rate as 0, we're going to add the rate constant or the rate laws of whatever is forming the diradical and subtract it by whatever the diradical is turning into. So I've written that down here. You notice this is from the first reaction, since the cyclo C3H6 is turning into the diradical, and then we subtract it by the reverse reaction, because that's what the diradical is turning into, and we subtract again the bottom reaction here, since the diradical is turning into propene. And we're saying that equal to 0, because it doesn't accumulate. So we're going to rearrange this to get all the diradical on one side, just to make our calculations easier and our substitutions to be possible. So we're going to add these two terms to this side, and we're going to get K1 cyclo, I'm just going to write cyclo for now, for shorthand, equals K-1 plus K2, and that's multiplied by our diradical. I'm gonna write diradical as dir for shorthand. So if we want to find the concentration of this diradical, because that's what we have in our initial rate law, we're just going to divide both sides by this. So we're going to get our diradical concentration is equal to K1 over K-1 plus K2 of cyclo. And here's where we apply another approximation. So in the problem, it says that K2 is much smaller than K-1. So if you notice here in our denominator, we have both K-1 and K2. However, K2 is much smaller, so we can essentially say that this is, or approximately equal to K1 over K-1 times the concentration of cyclo. And from here, we're going to substitute this back into our initial rate. So if you notice here, this was our initial rate law, and we have that the diradical here is equal to K1 over K-1 cyclo. And multiplying this by K2, dropping that down, we get K1, K2 over K-1 cyclo is our rate law. And if you notice here, that's the exact form here, except K is equal to this, which is K1, K2 over K-1, which is D. So that was a bit of a long problem, but it's quite nice when you get that solution. And if you didn't really read the problem that well, or you just didn't notice, and you didn't actually apply this K2 smaller than K1, you're actually saved here because there's no like K2 squared or anything funny like that. So yeah. So our answer is going to be D. And if you want to see like a formal solution of it, you can see this here. Now let's move on to question 30. So after that rough problem for the last problem, this is kind of like a more chill problem. We have that this reaction, doesn't really matter what the reaction is, but it has a product that is autocatalytic. You don't need to worry about this producing agent part. So essentially it means that as the product is produced, it's going to make the reaction faster. And that's shown in these Kinetics diagrams here. You have T versus the concentration of one of the reactants. So Essentially, a steeper slope here is going to mean that the reaction is going faster, and a more shallow slope is going to mean it's going slower. So let's just try to conceptually understand what this autocatalytic reaction really means. And all this is saying is that as the product is formed, the reaction is going to go quicker. So in the initial phases, the product isn't going to be formed that quickly. So the reaction is also going to go pretty slowly because that product is not catalyzing the reaction yet. Then the reaction is going to go quicker as the product is formed more. And finally, the reaction will slow as the reactants are going to be consumed. So summing it up, it's going to go from slow to fast and back to slow. So we're looking for a shallow slope to a steep slope back to a shallow slope. So let's go through these and see which best matches that description. Here we have a shallow slope, and then we have a steep slope, and here we have a shallow slope. So our answer is going to be A. However, I'm going to go over the rest of these and show why those are incorrect. Here it goes shallow to steep. It doesn't consider the fact that at the end the reactants are going to be mostly consumed, so the reaction is going to go slow despite the autocatalyzation. Here it's going to go fast to slow to fast to slow. That's just too many steps, an extra step here. Here this is just going fast to slow, and that's not going to match our description either. So our answer is going to be A.